All right, everyone. This notes is going to be all about ice tables. Ice tables are a continuation of the equilibrium constant calculation, which was in the note set that I had just filmed for you. So if you are somebody who is going to pursue AP Chemistry, if you are somebody who is going to go to college for a science-related field, ice tables are something that it's going to pop up a lot. So to start out, let's talk about what ice table means in the first place and what it even is. So an ice table is a method that we can use in chemistry to simplify certain calculations. And we can use them predictively because when we put concentrations of reactants into a vessel, into a container, at some point, if we're talking about an equilibrium system, it's going to stabilize into equilibrium. Those initial concentrations that we put in are going to change. And we can use an ice table to predict what our equilibrium concentrations of reactants in products are going to be. So ICE is an acronym. It stands for Initial, Change, and Equilibrium. So that I is going to stand for the initial concentration of reactants and products before the reaction starts. So if I have 2 reactant beakers in my hands and I have not mixed them yet, I'll have a certain concentration of both of those reactants in 0 products before I mix. C is going to stand for change in concentration, and that is how much the concentration of reactants and products is going to change during that reaction until it stabilizes in equilibrium. And those changes are expressed in terms of X. E is going to stand for the equilibrium concentration. And that is the row that would be plugged into an equilibrium constant equation or expression. And we did that a lot in the equilibrium constant notes, like we did a couple of practice problems about that. That row is what you would plug into that expression. And there's something else that I want to talk about really quickly, and that is small x approximation, which is going to be really important, and it's going to make the math for ice tables a lot easier. Because as you'll see as we go, if we're squaring x, if we're cubing x, if we're raising x to the 4th power or whatever, the math that we have to do can very, very quickly turn into quadratic equations. And to solve for x, you would have to use the quadratic equation to do so. And that's a long process. So to make our lives a little bit easier, if our KEQ value is smaller than 10 to the negative 4, so if it's a really tiny value or it's a really big value, bigger than 10 to the 4th power, then what we do is we assume that the change in concentration from reactants to products is negligible, which means that we can ignore it in certain situations, and I'll explain that as we come to it. So moving down first, we're going to do a practice ice table problem together. And then I'll go over a couple of examples. Now, again, we have an expression up here that is not at all a real reaction, obviously, WYZ. They're not actual chemicals, but we can use it to show you how this ice table is going to work. So from the last notes, I made my products were blue and my reactants were red, and I'm going to continue that through this ice table as well. So our problem says a sample consisting of 0.500 moles of W is placed into a 1.00 liter container. Use an ice table to calculate the equilibrium concentrations of Y and Z if the KEQ is 1.2 times 10 to the negative 5th. So right away, we're seeing that this KEQ value is really little. So we're actually going to use small x approximation in this ice table because 10 to the negative 5th is smaller than 10 to the negative 4th. So I'm just going to make that note before we continue. So to analyze some of the other numbers that we are given in this problem, it says the very first number we're given is 0.500 moles of W. And so that is a reactant number. W is our reactant, so that 0.500 moles is a reactant number, and it's in a 1 liter container, so we can do 0.5 divided by 1 to get that concentration of 0.5 molar. So I'm going to put that number here in my initial concentration, 0.500 molar, capital M. Initially, when I just throw my only reactant into this vessel, I don't have any products yet. I have 0 products whatsoever. And I know that because if I'm just holding a reactant and it's not doing anything, then I don't have any products. But over the course of this reaction, that is going to change. So I have to look at my reaction to figure out how it is going to change. So in my reactant, I know that as my reactant turns into my 2 products, as we go this way, I am going to lose some of that reactant. So I'm actually going to lose X amount of that reactant. So I'm going to put a negative X. But here's the interesting thing. If I have a coefficient, like I do here, that 2, I have to factor that into my change as well. So I'm not just losing X amount of reactant, I'm losing 2X of reactant because of that coefficient 2. Now for my products, I have to look at both of them separately. So for this column right here, I'm going to do the Y product. I know that again, as my reaction goes this way to the right, I am going to gain some product here. So I'm going to add a certain amount of both of them. And since my Y product has a coefficient of 2, I'm going to add 2X worth of that Y product. Z does not have a coefficient, which we know means that there's a 1 there. So I'm going to add 1X of my Z product. So what that means is that equilibrium, we are actually going to sum those 2. We're going to sum the I and the C boxes. So those 2 we're going to add together to be our equilibrium concentration. So if I add 0.500 and negative 2X, I get 0.500 minus 2X as my equilibrium. If I sum my 0 and my 2X here, I get 0 plus 2X, which we can just call 2X as my equilibrium concentration. And if I sum my 0 and my 1X, I'm going to end up with just my 1X there as my equilibrium concentration. So cool, I have all of that. I've done my ice table. But what I am asked to do by the product is to calculate my equilibrium concentrations of Y and Z. And so to do that, I'm going to need my KEQ value, which the problem gives me, and these equilibrium concentrations that are expressed in terms of X. So first things first, I'm going to write out my equilibrium constant expression up at the top here. I know that KEQ is equal to products over reactants. So I'm going to put my products, my concentration of Y raised to the power of 2, because again, it has a 2 coefficient, times my concentration of Z, not raised to a power because it does not have a coefficient. And I'm going to divide that by my concentration of W, and it has a coefficient, so I'm going to raise that to the power of 2. Now, I have that, which means that now I can start filling in some values into this KEQ expression. So my KEQ value, as I'm told in my problem, is 1.2 times 10 to the negative 5th. My 2 product concentrations, for my Y, it's going to be my 2X, and I'm going to square that whole thing. And then my singular X for Z. And that is all going to be divided by my 0.500 minus 2X, and that is squared. So this is my equilibrium expression with my equilibrium concentrations expressed in terms of X. So we got to do something first. I already told you that we are going to use small x approximation here, and that is a good thing. The reason it's good is because of this right here. If I were to square this entire thing, 0.500 minus 2x, I would end up with a quadratic. And you do not want to use the quadratic formula because that's really long and really annoying. So luckily we can 100% avoid doing that. Because if we assume that x's change is really, really small, then if I'm subtracting a really small value from 0.5, I'm pretty much going to be left with 0.5. It would round off to that using sig figs anyway. So we're going to just ignore this. And we're going to rewrite this entire expression ignoring that value of 2x there in the denominator. I am going to keep the ones in the numerator because I'm not subtracting or adding anything in the numerator. I'm just talking about x, so we can leave it there. So to rewrite it, I have my 1.2 times 10 to the negative fifth is equal to my 2x squared times x. So if I simplify that, that's just going to be 4x cubed on top. And then on the bottom, since I've ignored that subtracted 2x, I'm just going to end up with 0.500 raised to the power of 2. And so I can simplify that a little bit more just to make it look a little bit friendlier. So I still have my 1.2 times 10 to the negative fifth on the left, but I can say 4x cubed divided by 0.500 squared, which is 0.25. All right. So now I'm going to do a little bit more mathematical simplification. I am going to multiply that 0.25 on both sides. So if I rewrite this again, I'm going to end up with 3.0 times 10 to the negative sixth on the left. And all of that is still equal to my 4x cubed on the right. I can divide both sides by 4. I can rewrite this problem one more time as 7.5 times 10 to the negative seventh is equal to our x cubed. Now at this point, it's easy to solve for x if you know how to do it on your calculator. So if you're not sure how to do this on your calculator, I can show you in class, but we are actually going to take a cube root of both sides. So that's expressed like this. It's like the little square root symbol. We just use a cube root instead, which is again a function of your calculator. And we are going to get that x is equal to 0.0091. Okay, amazing. We've done that so far. Now, that is the value of x, but the problem doesn't want just x. The problem wants the concentrations of y and z at equilibrium. So we need to actually go all the way back over here to our equilibrium concentrations, and we're going to figure out y and z. We know that at equilibrium, the concentration of y is equal to 2 times x. So we know what x is now. So we can say 2 times 0.0091, and we can solve that out to be 0.018. And since this is a concentration, we're going to say moles per liter. For z, our concentration of z is actually helpfully equal to x, so I don't have to do any math whatsoever. I'm just going to say that x is equal to 0.0091, and again, that is moles per liter as my value. So this is my answer. So take a second. That was a lot. We're going to do another practice problem. Over here, we have iodine decomposes according to the following equation. We see that I2 is decomposing into 2 singular iodine atoms or ions. And so I'm going to circle my products with my blue. I'm going to circle my reactants with my red just to start out. I don't have a pre-made ice table, so you are going to absolutely draw one in. Pardon me if mine is a little bit messy and wonky looking. Initial change equilibrium. And then I am going to place my reactant and place my product up above their rows. Now, I have to interpret my problem a little bit. It says 0.36 moles of I2 is placed into a 4.5 liter flask. So in this problem, it's a little bit different because we're not in a 1 liter flask anymore, which means we need to figure out the concentration of our I2. So I'm going to use my red color. I'm going to do that math up here. Again, we know that molarity is equal to moles over liters. So I can do that. I can take my amount of moles of I2 and divide it by my liters. So that's going to be 0.36 divided by 4.5. And I'm going to get a concentration of 0.080 molarity, or moles per liter. That is the concentration right here that I am going to plug into my initial box for my I2. All right, next, it says if my KEQ value is 2.94 times 10 to the negative 8th, calculate the equilibrium concentrations for I2 and I. So once again, we are seeing that our KEQ value is really, really small. So I can use my small x approximation, which makes our life happier and our math easier. So going back to my ice table, I know that if I am only placing some reactant into my vessel, I'm not going to start out with any product whatsoever. Those two values, reactant and product values, are going to change in terms of x. So I want to look back up here at my reaction. There is no coefficient in front of my I2, so that is going to change in terms of just a singular x. So we're going to lose x amount of my I2. There is, however, a coefficient up here in front of my singular I, so we are going to gain 2x worth of I. Then, just as we did before, we are going to sum those two boxes together to get my equilibrium. So on the left here for I2, we end up with 0.080 minus x. And in my products, I end up with 0 plus 2x, which just leaves us at 2x. Now I get to plug all of that into an equilibrium expression. So my equilibrium expression is going to be KEQ is equal to, again, products over reactants. So I have on my product side my concentration of I raised to the power of 2 because of my 2 coefficient. But down below, I have my concentration of I2 not raised to a power because there is no coefficient here. And then I can go ahead and start plugging in my values. My KEQ value, I am told already, is 2.94 times 10 to the negative 8th. And that is going to be set equal to my equilibrium concentration for my product. So that's going to be my 2x. And again, I'm going to square that because I did in the equilibrium constant expression. And I'm going to divide that by my I2 value, which is my 0.080 minus x. Once again, I already said, hey, guess what? I can use my small x approximation, so I can go ahead and ignore that little value of x just to make my own math easier for myself. I can go ahead and rewrite this. 2.94 times 10 to the negative 8th is equal to, simplifying the top of my fraction, I end up with 4x squared on the top. On the bottom, I just have 0.080, and then I can go ahead and mathematically simplify and solve for x. So just take you through the rest of those steps. We have our 4x squared on the left. I multiply both sides by 0.080, and I end up with 2.4 times 10 to the negative 9th on that side. I'm going to end up dividing both sides by 4, and then I'm going to end up with x squared, whoops, wrong color, x squared on that side. Once I divide both sides by 4, I'm going to end up with 6.0 times 10 to the negative 10th. That means I'm going to root both sides, not a cube root this time, just a regular square root. And over here, I'm going to get x is equal to 2.4 times 10 to the negative 5th. So next thing is to calculate the equilibrium concentrations for I and I2. So I have to go back to my equilibrium concentration box, and I'm going to do I2 first. That is equal to 0.080 minus x. So I'm going to subtract my 2.4 times 10 to the negative 5th out from that. And you will find that, hey, guess what? Shockingly enough, subtracting a number that tiny from 0.080 actually still does round to 0.080, and that is moles per liter. For my I concentration, so that's going to be my product, this one, I find that that is equal to 2 times my x value, which was 2.4 times 10 to the negative 5th. And so I can say that that is 4.8 times 10 to the negative 5th, and that is, again, moles per liter. And again, we have another done ice table. It's a lot, I know. At this point, if you want to, on your own, I would encourage you to do this one by yourself. It is a little bit different, but at least give it a shot, just so that you can try to figure it out. But that said, if you would feel more comfortable with just watching me do it and copying that down, that's fine too. So once again, we are going to start by analyzing our reaction that we are given right up here. I'm going to go ahead and circle my reactants in red, circle my products in blue. I'm going to write an ice table just because I know I'm going to need one eventually. And I am going to copy down my reaction, my H2, my Cl2, and my 2HCl. All right, so I've done all of that. Let's analyze the problem. It says if we start with 0.020 moles per liter, so that's a concentration already, of hydrogen and chlorine. So I'm actually given my initial concentrations of both of my reactants and 0.00040 moles of hydrochloric acid. So this one is interesting because I am actually given initial concentrations of reactants and products. So whereas before I was just given reactants and assumed 0 products, this time it's not the case. So since all of those are given to us in the form of concentrations, you can actually just go ahead and plug those straight into the initial row of our ice table. So these first two are both 0.020, and then our product one is 0.00040. Once again, we're going to express our change in concentration in terms of x. Neither of these reactants up here have a coefficient in front of them, so we are going to lose some amount of x. And then our product does in fact have a coefficient in front of them, so we're going to gain 2x. Now, once again, we are going to sum initial and change together to make equilibrium. And so in both cases for H and Cl, we have 0.020 minus x in both of those. For our product, we end up with 0.00040 plus 2x. Sorry if that's a little bit small, but again, we're just summing those up. Now, we are going to write out our equilibrium expression, and I want to point this out too. This is not small x. So we cannot use small x approximation for this one. So this one might be a little bit harder to solve, but don't worry, I will walk you through it. I know that my KEQ value is still, as always, equals to products over reactants. So my product is my concentration of HCl raised to the power of 2 because of this coefficient. I'm going to divide that by my reactants, my concentration of H2 times my concentration of Cl2, neither raised to a power because they are not in possession of any coefficients up here. To rewrite that a little bit, I need to actually use my equilibrium constant. So my KEQ is 0.0036, and that is equal to my concentrations expressed in terms of X. So on top, I have my 0.00040 plus 2X squared. And then on the bottom, I have my 0.020 minus X, and that is actually also squared because really we're counting that twice because we have our H and our Cl2 and both of those were the same, so I just went ahead and squared it right there. Now, obviously we have two squared things, and that could theoretically present a problem, but the really nice thing about this problem in particular is that both of those are squared. So what we can do to make our own lives easier is we can actually just go ahead and square root both sides of this equilibrium expression to just get rid of those squares and not have to deal with the quadratic formula. So I go ahead and rewrite that. The square root of our equilibrium constant ends up being 0.06, and we are now equal to, on the top, just 0.00040 plus 2x. Let me extend that line a little bit. Then on the bottom, we just have our 0.020 minus x, and I've gotten rid of all of those squares. Now, all we need to do is mathematically rearrange it, so I'm going to kind of summarize that a little bit and do a couple of steps, but not show every single one because I will run out of room if I do that. So initially, I'm going to end up on the right-hand side by multiplying this thing on both sides. So I end up with 0.0012 minus 0.06x on that side. And then on the right-hand side, I still have my 0.00040 plus 2x. Then I can simplify a little bit further, move some stuff around mathematically, and I can say that 0.0008 is equal to 2.06x, and I can get an x value equal to 0.00039. Now, from here, we are going to go ahead and just solve the problem out normally. It asks, what are their equilibrium concentrations? So I want the equilibrium concentrations for every single thing in this. So I'm going to go ahead and start with H and Cl2 because both of those have the same exact equilibrium expression in terms of X. So I can say that my H2 concentration and my Cl2 concentration are both equal to 0.020 minus my X value, which is 0.00039. That is going to be equal approximately, again, to 0.020 because realistically I am subtracting out a number that is so small that using sig figs I'm going to end up rounding to that initial value anyway. So that is going to be moles per liter. Again, it's a concentration. For our product, we know that our HCl concentration was equal to 0.00040 plus 2x, which, subbing in my values, I get 0.00040 plus 2 times 0.00039, and then if I solve that out, I get 0.0012, and again, that is moles per liter. Here is your answer for this ice table problem. Here's the notes as a whole. If you would like to see all of them all together, I hope this was helpful. Again, this is quite a challenging problem set to do, so if you have questions, please come talk to me.